So today I'm going to be talking about the paper RBJ25 cryptographic algorithm for securing big data, written by S. Rajaprakash et al. So basic introduction to the paper, like what all we're going to cover in this PPT is written here in this contents. So first we'll go over the abstract of the paper, then we'll go to the problem statement, the implementation, and the future scope of this particular cryptographic algorithm. So let's first go to the abstract. So if we talk about the abstract, it talks about, firstly, we need to know what cryptography is. So cryptography is basically the practice of securing communication from unauthorized access. Cryptography basically involves techniques for encrypting messages, digital signatures, and authentication. It provides confidentiality, integrity, and authentication of data. And it can be classified as symmetric or asymmetric, and it depends on the type of key used, which is if we're using only public keys or public and private both. Symmetric key basically involves a shared secret key for both encryption and decryption, while asymmetric key involves a public and private key pair, as I mentioned. So cryptography plays a critical role in securing online transactions, communications, and data storage, and it's constantly evolving, and new techniques and algorithms are being developed to counter emerging threats. However, many cryptographic methods that are already present are being used in web applications, but they're not able to ensure informational collections. The data that's being collected, it's not able to properly ensure that they are in secure hands. So this is where our problem statement lies. So we have a few problems in the crypto systems that we'll analyze here that were given in the paper. So firstly, there's fault attack of Cha-Cha algorithm. So fault attack of Cha-Cha algorithm basically involves inducing a fault during the encryption or decryption process to reveal the secret key or plain text. So the attacker exploits the non-linear operations of the algorithm to manipulate the data and cause an error, which can be used to infer information about the key or plain text. So this is a drawback of using the Cha-Cha algorithm. Secondly, we have the bricklayer attack. So bricklayer attack is basically a type of cryptanalytic attack that targets block ciphers mainly, and it modifies or deletes blocks of encrypted data. So the attack seeks to manipulate the cipher text to cause changes in the plain text without knowing the secret key, and thus compromising the security of the system. Then we have fault injection attack, which is a very interesting one. So fault injection attack is a type of attack that targets a system's hardware or software by deliberately inducing faults or errors to compromise its security. The attack basically exploits vulnerabilities in the system to alter its behavior and reveal sensitive information or gain unauthorized access. And lastly, we have power analysis attack on SALSA 20. And it's a type of side channel attack that targets the SALSA 20 encryption algorithm, and it analyzes the power consumption of the device during the encryption process. So the attack exploits the correlation between the power consumption and the algorithm's operations to extract the secret key, and it compromises the security of the system. So we can see two mainly used algorithms, Cha-Cha algorithm and SALSA 20, have these four particular problems. However, there are also solutions provided in the paper to counter this. So since they're widely used, obviously there's a solution to counter these problems. Fault attack of Cha-Cha algorithm is overcome by freestyle method, which is basically hash-based halting and key guessing. So that's how you that's the first solution to the first problem given here. Then you have secure mode for bricklayer attack. You have secure modes of operation, like you choose to do secure modes of operation. You randomize the plain text so they're not able to modify the block, and you do strong key management and MACs. So by implementing this, you will be able to make sure that the messages are the integrity of the messages is maintained, and you can't modify or delete any block of encrypted data. In fault injection attack, to prevent this, you have redundancy and error correction, which you can basically do through checksum. You have randomization of a particular key or something. You have fault injection detection mechanisms. So this is a very important part in solving the fault injection attacks. It basically incorporates fault detection mechanisms in the system and can help identify and respond to fault injection attacks. So it's basically like an IDS and IPS mechanism, like adding integrity checks, monitoring the system for abnormal behavior or error rates, implementing watchdog timers, and etc. can help and detect and mitigate the effects of fault injections. And for power analysis attack, we have the solution of constant time, masking, randomization, and security evaluations. So masking is the important term here. We can take an example like we can apply random mask or blinding factors to sensitive variables to make the power consumption patterns unpredictable and prevent the attacker from extracting information about the key. So these solutions are provided in the particular crypto systems that we've seen here, the attacks that we've seen here. However, there are still a lot many underlying faults and attacks that cannot be addressed, and some solutions do not exist. And of course, like with the rising rates of cybercrime happening, we can always find some tool or some method or algorithm that surpasses these particular crypto systems. Therefore, the writer of this paper intended to use a particular new algorithm, and they developed a new algorithm. So that's what we're going to see, which is the RBJ25 cryptographic algorithm. So as I've mentioned, to overcome these before mentioned problems, the paper developed a new cryptographic algorithm, namely Rajaprakash Bhagat Bhasha Jaishankar 25. It's a handful. So this algorithm RBJ25, which it works on the matrix of order n, so it's basically a square matrix of order n by n. It has three main processes to carry out the cryptography, which we'll see now. So it's got three processes, but the third process have 5 sub-processes. So these are the processes that we'll see. So the first process is column operations in the matrix. We basically perform simple column operations in the matrix. All the implementations will be seen in the coming slides. The second process is secret key multiplication in the matrix. You basically take a random secret key and you multiply it on the entire matrix. And RBJ25 with matrix n cross n that we've already discussed, it's a square matrix. So we go to the third process and it has 5 sub-processes. So in all, we have 7 total processes. First process of the third process subtree is analyzing possible prime numbers in the given matrix. So for example, you take all of the numbers present in the given matrix and you analyze what are the possible prime numbers, like we take factors and we analyze what are the possible prime numbers that we can take in the given matrix. Then we apply possible prime numbers in a quadratic equation that is already defined. We merge all the numbers into a single row and we form a pair from so the 3.31 is actually, we apply it in a quadratic equation, we get a particular answer to that, and we negate the floating point, like we negate the decimal, and we just take all the numbers as it is and merge it into a single row. So we get a huge integer number, and then we form a pair from left to right from third process that we've already got. The merged numbers we've got in a particular row, we will form a pair from left to right. So for example, we can form a pair of two numbers from left to right. And then we swap cell values with the help of pair from matrix. So the pair that we received in the process 3.4, for example, if we receive 1, 2, 4, 5, so we swap the cell values, which is basically the matrix value at 1 and 2 are swapped with each other, and 4 and 5 are swapped with each other. So after doing that, we'll be able to have an encrypted matrix. So let's look at the implementation here. I'm using the example that they've already offered, but we are free to take our own examples. So the first step is basically column operations that we've seen here. So here it basically talks about CA, which is a column encrypted matrix that we want to achieve. CI is the matrix that is available to us, and we are basically exchanging the column numbers. So I plus n minus m, we are applying this operation. So it basically like reverses the matrix in a way. So for example, if you have 1 2 3 4 5 6 7 8 9, so it will reverse the matrix, like it will print the opposite of this in each row. So 3 2 1 6 5 4 9 8 7. So the entire matrix is reversed. Then we have step 2. We get this matrix 3 2 1 6 5 4 9 8 7 from the previous step, and we apply a secret key. So we do secret key multiplication in this particular matrix. So we have A as the matrix that we got from the previous step, and we do secret key EK into A. So we basically multiply it, and matrix multiplication is simple. You simply multiply the number with all elements in the matrix. So you multiply the secret key in the matrix A is the matrix, and EK is the encryption key. So you can see if we've taken the encryption key as 5, 5 will be multiplied to all of these values, and we'll get the matrix as 15, 10, 5, and 30, 25, 20, and so on. So you can see we are getting these values, and this will be our matrix now. After going to step 3, we have to do prime number analysis in the matrix. So we have these numbers present in the matrix. Now we need to figure out what are the prime numbers that we can get out of this. So after applying this step, we get possible prime numbers as 2, 3, and 7. So 7 you have from here, this is 5 into 7, so you get 35. We have 7 from here. 2 we have from, you can take from any 10, 20, 30, 40. You can have 2 as a factor in all of these. And 3 we have 5 into 3, 15. So we can have 3 from here. Right. So we get 2, 3, and 7 as the possible prime numbers in this particular matrix values. So we have the prime numbers. Now we have to apply these prime numbers in a particular quadratic equation that we see here. So EM is the encrypted matrix that we want. ABC are the possible prime numbers. So A, B, C are all used here. The formula is minus B plus minus B square minus 4AC root divided by 2A. So the possible prime numbers we got were 2, 3, and 7. So you basically take A is equal to 2, B is equal to 3, C is equal to 7 in a particular order. You can take random as well, but we choose to do this one here. So you apply it in the equation. So B is 3 here, so minus 3 plus minus 3 square minus 4AC, which is 2 into 7, 4 into 2 into 7. So this is square root of this entire thing. And this entire thing is divided by 2 into A, which is 2 into 2 here. So after calculating this particular value, we get minus 3 plus minus 6.85565, and the entire thing divided by 4. So this is the particular encrypted matrix that you've got. So this is the formula that you've got after adding the prime numbers into the quadratic equation. So this concludes step 4. Now we go to step 5. So we have EM here. Now what I had mentioned is that we had to merge all the numbers into a single row. So what you have to do basically, so you see these are the particular numbers that you see. Like normally we just go with minus 3 plus minus 6.855 something divided by 4. But we're not gonna look at the negatives or the signs or the decimal points or division or anything like that. We're just gonna take the numbers, extract the numbers out of this equation, and we're gonna add it into a row. So after applying step 4, we get 3, 6, 8, 5, 5, 6, 5, 4, which is here 3, 6, 8, 3, 6, 8, 5, 5, 6. Sorry, I think I made a mistake here. 3, 6, 8, 5, 5, 6, 5, 4. So this is basically the number that you get. These numbers are the same. I made a mistake while reading this thing, I think. So after applying step 4, you get this one, and that's basically step 5, which is merging all the numbers into a single row. Now you go to step 6, which is forming a pair. This is pretty easy. You basically first you have to ensure that these numbers come in multiples of 2. Like if you divide by 2, the like if the length of this is divided by 2, you get 0, like mod 0. So mod of this entire thing, like the length of this entire thing is 0, sorry. So otherwise you can just use padding bits, like you can add a 0 or something in between or at the end. And we basically form a pair of numbers from left to right from step 5. So step 5 we had got this thing that we've carried forward here. So after applying step 6, we will get 3 6 8 5 5 6 and 5 4. As you can see, 3 6 8 5 5 6 and 5 4. So these are the pairs that we received, and now we go back to our matrix. So each and every pair should swap cell values from the given matrix. This is basically the starting of the step 7. So as I told you, step 7 is divided into a number of steps. Actually, it starts from step 3 only that we've talked about. Step 3 has been divided into 5 steps. So this is the last step of step 3. So you basically swap all the values and then you'll get the final output. So we'll be seeing this here. So these are the pair of numbers. We're going to remember the first one itself, and after that we'll see. So 3 6 is the first one being used, and we'll see our matrix given here. This was the matrix that we received at step 2 or step 3, I think. So yeah, step 2, sorry. We had multiplied the private key with the matrix. So we have received this matrix. We have multiplied 5 with the entire matrix. So now we remember the first pair is 3 6. So this basically says the first pair number 3 6 should be swapped in the given matrix, and this matrix represented starts from 0 and goes to 8, because there's 6 elements here. 0 1 2 3 4 5 6 7 8. Sorry, 9 elements here, my bad. 0 1 2 3 4 5 6 7 8. So there's it goes till 8 here. And if we get a 9 value in this pair, then we just reduce it by 1. So we'll use the 8th value instead of the 9th value, because it'll be out of the index if we use the 9th value. So this covers all the numbers that are there in the decimal system, the pairs that we formed. So from 0 to 9 basically. So the only exception is that if we get a 9, we'll use the 8th value. So we first formed the first pair number, FPN, and we have to swap 3 and 6. So we had 0 1 2 3. So 3 is 30 and 4 5 6 and 6 is 45. So we have to swap 30 and 45 together. After that we'll get this particular matrix. So you can see 15 10 5 as it is, 45 and 30 are swapped, and then 25 20 and 40 and 35 as it is. So this is the first pair number that you get, which is referred to as FPN in this particular paper. Then you continue, you swap the second pair. I'll show you the second pair that we had. You can see 8 5 is the second pair of numbers that we had. So you go and swap the second pair, 8 5. So 8 is 35 over here. We have taken the first pair number matrix from the previous one. So all these operations are being performed on the previous one. So how many number of pairs you have, you perform all the operations in the previous matrix that you've got, the result of the matrix that you've got after swapping. So 8 5 should be swapped. So you go to 0 1 2 3 4 5. So 20 and 6 7 8 35. So 20 and 35 are going to be swapped here. So you can see 15 10 5 as it is, 45 25 as it is, 35 and 20 have been swapped, and 30 and 40 as it is. This gives us the second pair number matrix. Now we have 5 6, which is third pair number, and we'll have one more after that. So 5 6 should be swapped, and this is basically, I think, 30 and 35. Let me count again. 8 7 6 and 5. Yeah, 6 and 5, 35 and 30. So 35 and 30 are going to be swapped, and it gives us the third pair number. And 35 and 30 are swapped, rest the values are as it is. Next we have the fourth pair. In a similar fashion, it's pretty easy. The elements are just being swapped. It's a very light program to write as well. You can implement this pretty easily if you know NumPy. In Python, you can easily implement this matrix, and element swapping is pretty easy. So 5 4 should be swapped from the third pair number matrix. So TPN we have taken from the previous one. So 5 4 0 1 2 3 4 5. So 25 and 30 are going to be swapped, which you can see here. And FOPN, which is the fourth pair number, is our final matrix, because we've used all the pair numbers. So fourth pair number is our final encrypted matrix. So this is what you get. As a comparison, I've added actually I haven't. So you can see we started off with 5 10 15 something like that. I'll just show you actually. We start with 15, 10, 5, 35, 30, 25, 20, 45, 40, 35. Basically 5, 10, 15, 20, 25, 30, 35, 40, 45, like in the opposite order. So, and we'll get fourth pair number as 5, 10, 15, 25, 30, 45, 20, 40, 35. So like it's a bit scattered. And the more pair numbers you used, like this has a little drawback that the pair numbers, if they are like similar in the result, then we can get a matrix that is similar to the matrix that we actually had, which is one of the drawbacks of this system. But as for speed and efficiency, this is pretty much the fastest for encryption and decryption, which we'll see later. But certain drawbacks also exist in this particular method, and it is a fairly I would say like easygoing method that can be used. But yeah, like for understanding purposes, I think it would be like really great. I would doubt for the implementation, because other algorithms have higher complexity than this one. So the future scope of this particular project, the research paper that they've written. So with exponentially increasing file size, the performance of our RBJ25 algorithm does not deteriorate, as it is very simple and lightweight. And the encryption and decryption speed is better than both AES and Cha-Cha encryption algorithm. Although the reason why Cha-Cha algorithm and AES are still running in the current scope of cryptography and cybersecurity is because they are basically uncrackable. There are faults and there are attacks and there are vulnerabilities in this particular algorithms, but till now AES has not been cracked. Or if you're talking about RSA has not been cracked yet. So like RSA is basically a secret key exchange, a secret key generation algorithm. But still, like if you're talking about a particular algorithm, the complexity matters. It's a directly proportional relationship. Like if you go higher in complexity, your speed will decrease. So I would say inversely proportional. So yeah, if you go higher in a particular complexity or unbreakability of an algorithm, your speed of processing like encryption and decryption will obviously increase. That's a direct proportional actually. Yeah. So we need to have a balance between all of that, and RBJ25 is I would say very less secure, but has a really great speed. So like if you're applying some sort of signature or something like that, and you just want to encrypt it with a short lightweight algorithm, I think RBJ25 would work great with that. And so you have encryption and decryption speed here. So we can compare the speed and visualize it in bar graph, which is given in the following slides. All of these are taken from the research paper that has been provided. So you can see this is a comparison of Cha-Cha, AES and RBJ25, and this is the encryption speed that we're looking at over here. So you can see encryption speed is in seconds over here. So if you're talking about Cha-Cha algorithm, we can see an average of about like 1.5 or something as the encryption speed. As the file size increases from 2476 111, it goes till 6580, which is in bytes, by the way. So the encryption speed is like shown as it is. So we can see that RBJ25 has the highest encryption speed as compared with Cha-Cha and AES, as they obviously have like as the file size increases as well, they have like they take a lot of time as to encrypt, especially if you're talking about block ciphers here. Technically we're talking about block ciphers here because RBJ25 also uses a 3x3 matrix, like we've used an n×n matrix. So we're talking about block ciphers. We're not using it as a stream cipher. And so you can see the encryption speeds are significantly better for the RBJ25. If we're talking about decryption speed, we can still see that RBJ25 is highly accurate for all the file sizes. Now, as the file size increases, here you can see that it's at the lower file sizes, the encryption speeds are very comparable with AES, which is actually good, that AES actually performs better in like lower file sizes. But as we go higher, AES still stays the same when performing decryption. And while RBJ25 performs like overly over the limit, like it's way better in performance than Shasha and AES. So this is basically the encryption and decryption speed of the RBJ25 algorithm, and hence it's like a lightweight, easy to implement algorithm that can be used for crypto systems. And I would suggest like it would be useful in encrypting small chunks of data, or like applying very lightweight security into your transmission. So that is the conclusion of this short summary of the RBJ25 cryptographic algorithm for securing big data. Thank you.